Good morning. We are today looking at chapter 31, and we're going to wrap things up as far as looking at electric and magnetic forces and fields, and this is kind of the end of that section of the course. So chapter 31 is called Maxwell's Equations and Electromagnetic Waves. Not sure how I feel about this title. So what's going on in this chapter is looking at the acceleration fields that we've been talking about. So we've mentioned a few times the importance of these acceleration fields. We saw them when we were looking at inductance. And now what we're going to show is that when charges are undergoing an acceleration, they generate electric and magnetic fields that actually are able to carry energy away from the charge. So we can actually transfer energy or radiate energy away from charges that are undergoing accelerations. And this is what our communications devices use. When we're looking at signals coming from radio stations or signals with cell phones and cell towers, something in the radio part of the spectrum, something in the microwave part of the spectrum, and even infrared and visible light and beyond, these are electric magnetic fields that are propagating away from some kind of a source. So let's take a look and see how we're going to wrap things up here with these fields. Now there's kind of two different ways of looking at this. Kind of the standard way to introduce the idea of electric and magnetic fields that are propagating is to bring out what are called Maxwell's equations. Now, just very quickly, back in chapter 22, we introduced Gauss's law, and we used that to be able to calculate electric fields surrounding spherical devices or cylindrically symmetric devices or planes of charge. What we didn't do at that time was point out that there's also a Gauss's law for magnetic flux, but the magnetic flux is always equal to zero. And that's just saying that magnetic field lines are always looping. We don't have examples of magnetic fields where the magnetic fields are directed away from a source. And then we had Ampere's law. Ooh, I guess that's here. Ampere's law in chapter 28 maybe. And then finally in chapter 29 we had Faraday's law. So these are considered to be the complete set of these four equations are considered to be Maxwell's equations. And if you're a clever enough mathematician, these integral versions of these formulas, notice that we've got the integrals on this side, we have the time derivatives over here, will tell you how to work from the Q's, the charges, and the currents, and derive what the electric and magnetic fields are. Now, I'm not that clever of a mathematician. Maxwell's equations can certainly work from Maxwell's equations, but I don't feel like it's the clear, obvious way to think about how these fields are behaving. So anyway, here is that Gauss's law for magnetic fields that we talked about, and this is analogous to Gauss's law for electric fields. So let me kind of outline at least my view. I think in some sense, if you're a science major and you've taken physics, you're supposed to at least be familiar with the term Maxwell's equations. So James Maxwell, during the mid to later 1800s, took kind of all of the information that had been developed through researchers doing a lot of research into electric forces, magnetic forces, electric and magnetic fields, and Maxwell was able to mathematically provide a systematic framework representing all the different fields and how they were related. So Gauss's law for the electric fields is actually telling us how electric fields are, well, diverging. So how the electric fields are directed away from a source of positive charge and equivalently how they're oriented towards a region of negative charge. And so that's considered one of the four Maxwell equations. The second Maxwell equation, the Gauss's law for magnetic fields, says there's no such thing as diverging magnetic fields. We don't see examples of where we have individual charges with magnetic fields directed away from them. Those sorts of diverging magnetic fields just don't occur in nature, and they're not expected to occur. It's not like something is missing there. Then we move on to a couple of these path integrals. Now, this one, I guess we want to look at. This was Ampere's law, and it says that we can relate magnetic fields to currents. And so back in chapter 28, we said if there's a region that currents are passing through, did I write that as, oh, I see. If there's a region where the currents are passing through, we are going to end up with looping magnetic fields. So this says, these are examples of looping magnetic fields, and they're related to the motion of charges. And then along with that, what we can also generate at the same time from these charges are electric fields that could have, that could be varying. So it could be that I have a combination of currents, varying electric fields, and looping magnetic fields. Now this is where I just don't think these are as useful. The Maxwell equations are very useful for a first pass through electric and magnetic fields, looking at electric and magnetic forces. Also, there's Faraday's law that says there's a relationship between looping electric fields and magnetic flux. So if I have a region of magnetic field flux that's varying, that's going to be related to electric fields. Now the force constants that get used in our book, the book has been using epsilon naught, 1 over 4 pi k, and mu naught, 4 pi k over c squared. And then the textbook suggests, incorrectly, that epsilon naught times mu naught is a way of predicting the speed of light. And that the speed of light can be derived from that. And I'm going to say that's not quite the way to think about it. What we should really do is think in terms of, well, what are the fundamental constants here? The fundamental constants that we're working from are c. Now c we've talked about as not just the speed of light, but c actually has to do with how space and time are put together. It turns out, surprisingly, that space and time have this mathematical connection between the two, and that when we work in four-dimensional space-time, we need some kind of a factor that will tell us how many meters of space are related to how many seconds of time. And that's what c is. So c is just a very fundamental constant about how space and time are constructed. So it's not like we can derive c from that. Now what we can do is we can do a series of experiments of electric and magnetic forces and do measurements of those to come up with a value for c. So we can do measurements based on electric and magnetic experiments, but we're not really deriving c from that. C is actually the more fundamental constant. Now the other fundamental constant here is we need a force constant that tells us how strong the electric and magnetic forces are in nature. And so what we have at this point is a consistent mathematical description of electric and magnetic forces based on special relativity and based on the correct space-time properties that we observe. And so I'm going to say these are the two fundamental constants. C is telling us about how space and time are put together, and K is telling us how strong the electric and magnetic forces will be. Those are the two fundamental starting points. So I'm going to claim that epsilon naught and mu naught actually get derived in terms of the more fundamental constants. Okay, that's my bias for all of this. So I'm going to say that rather than starting with the Maxwell equations to determine fields, what we can do is come up with formulas for the electric and magnetic field for charges that are moving with some velocity. So depending on what that velocity is, and we've seen these equations before, this formula tells us what the electric fields will be, this tells us what the magnetic fields will be. And an important feature of these velocity fields is that they drop off like 1 over r squared. That means that as I move farther away from the charges, the fields actually get quite a bit weaker pretty fast over not such large distances. The electric and magnetic fields will drop off. Now what we're really interested in is looking at energy densities. So how fast will the energy densities drop off if we start moving away from those charges? And if you remember, the energy densities are found by squaring the magnetic and the electric fields, and that says that they drop off really fast, 1 over r to the 4th. So if I get away from a bunch of charges, the velocity effect of the fields, the velocity fields are going to be pretty small. In addition to the velocity fields, however, there are what we call acceleration fields. I didn't even notice that the slide changed, right? Anyway, I went from saying velocity fields to acceleration fields. And we also have electric and magnetic field components that are determined not by the velocity of the charge, not by how fast it's going, but what its acceleration is. And these also are kind of instantaneous formulas. And so the magnitude of the acceleration electric fields, kq over r, it's proportional to the acceleration, c squared, sine theta, where sine theta is the angle relative to the direction of acceleration. So if I have a charge accelerating in this direction, it's going to generate those velocity fields because it's moving, but it's also going to generate these acceleration fields because it's accelerating. And based on its acceleration and based on the formulas we have here, what we find is that the electric component, magnitude, and the magnetic field component, they match. So what's going to happen is that we'll have equal magnetic and electric fields, and we'll have equal contributions to the energy density. For acceleration fields, the energy being carried by the electric field components matches the energy being carried by the magnetic field components. Also, we have the same 1 over r dependence, and we have the same sine theta dependence. So it says that if I've got an accelerating charge, the energy density out ahead of the charge that's propagating away from the charge is not as large as what it is to the sides. So the largest electric fields and the largest energy densities are going to actually be radiating away from the accelerating charge sideways. It's the sideways directions where most of the energy ends up traveling with these. Okay, so a lot of times students, when they come into chapter 31, they go, isn't this like a new set of rules for the electric and magnetic fields? It seems really different from what we've done before. And that's because textbooks fail to point out that we're no longer looking at the properties of the velocity fields. We have moved on, and now we're looking at the properties of what we call the acceleration fields. Now, once we write down the formulas for both the velocity fields and the acceleration fields, I think that's a more direct way to think about how these fields work. How are these fields being generated? Than Maxwell's equations. Maxwell's equations will give us an equivalent set of information about the fields, but I always feel like mathematically Maxwell's equations are a little bit beyond, Maxwell's equations are a lot more challenging, a lot more difficult to build an intuition for. So the next slide that came with the text, and I also have to point out, I think our textbook is great. I wouldn't be using it unless I thought that the textbook we have really explains things well. But as you would imagine, with any any textbook you're going to work from, there are going to be times when probably disagree with the way some of the information is being presented. Now, this is a very common statement that we say in physics, and you may have heard this in physical science courses that you've taken. Changing electric fields produce magnetic fields, and changing magnetic fields produce electric fields. So I had to cross it all out with some red marker. That's not really true. They're associated. So if I have a region where electric fields are varying, there will also be magnetic fields present, and vice versa. But that's not really what's causing those electric and magnetic fields. The magnetic fields are coming from charges, and those charges can be at rest, they can be moving at some velocity, they can have some acceleration to them. In order to determine what the electric fields will be and what the magnetic fields will be, I have to know what's going on with the charges. The charges are the source for all the electric and magnetic fields, not other fields. Okay, so let's move on and take a look at what generating the fields might look like. This is actually calling it the production of electromagnetic waves. Now, what they're calling electromagnetic waves, the word wave always makes me nervous because when we say wave, all we're really saying is that these electric and magnetic fields that are being generated by these charges are propagating away from the source, away from the charge. So what does happen with electric and magnetic fields is that the effect of the electric and magnetic field actually propagates away, and it propagates away at c. It propagates away at the speed of light. So if we have charges, for example, that are oscillating back and forth. Let's say we have a region where the charges are oscillating back and forth in an antenna. What's going to happen is we are going to generate electric fields. So what this picture is showing is currently, right at this time, the current, it's not just that the current is moving in this direction, it's that we have an acceleration in this direction. So if we have an acceleration of the charges, the current is increasing in that direction, we're going to get electric fields that wrap around that region, and they're going to wrap around that region in a direction that opposes the acceleration. It's going to be in the opposite direction to the acceleration. Now when we get this set up, we're also going to have magnetic fields. The magnetic fields shown here are into the page or out of the page. Now the orientations that we've got here for the magnetic fields, if you trace these back, they're given by this diagram. So when I have a charge that's accelerating in this direction, the electric fields surrounding that charge wrap back around the direction of the acceleration. Meanwhile, if I've got an acceleration in this direction, the magnetic fields are forming right-handed loops around that direction if the charge is positive. If the charge is negative, they're forming left-handed loops. Okay. So when we switch this over to an antenna, what that says is, if I have charge that's accelerating in this direction, I'm going to have E fields that wrap around the direction of charge, and I'll have magnetic fields that form right-handed loops around the direction of acceleration. That's what's going on. Okay? So it's the accelerating charge producing these acceleration fields, and that's the orientation of the fields. Now, the feature here, did we get this mentioned? Let's see. The real feature of these acceleration fields is that the fields don't drop off as rapidly, and the energy densities are only dropping off like 1 over r squared. And what that results in is that these fields actually carry energy away from the charge. I think we said that. So what happens with these acceleration fields is that, well, this is light, actually. These are particles of light, photons. When we use quantum mechanics to describe what this field consists of, the electromagnetic fields consist of particles of light, and we call those particles photons. Now, when we say light, we're not just referring to visible light, we're referring to the entire spectrum, all the possible different energies of photons. And so this includes radio, microwave, infrared, visible light, UV, gamma, X-ray. So the whole spectrum gets included in this. And again, if I have accelerating charges as a source, there's a net energy transfer away from these accelerating charges. Now, if the charges are oscillating, that's one form of acceleration, then what's going to happen is, as the electric fields propagate away from those charges, they're going to alternate the direction of the electric field. So when the acceleration was in this direction, an electric field in the opposite direction was produced. But when the acceleration switched, well, the electric field switched. So if the charges are oscillating, then the electric and magnetic field will show the pattern of oscillation. So waves don't have to be wavy, as one student from a few years ago liked to say. Waves just mean that the energy is propagating away. It doesn't have to have the form of a wave. The reason that we very often draw the electric and magnetic fields in kind of a wave shape is because we typically produce these radio and microwave photons, electromagnetic fields. We typically generate them by using oscillating charges. Okay, so here's another attempt at one of those pictures. That's the picture we were looking at earlier. So what's happening in my antenna is I'm oscillating charges back and forth, and that means that the acceleration is in this direction for a while, and then it reverses and goes the other way, and then it goes back the other way. And what that results in are electric and magnetic fields, which, as I look downrange away from the antenna, are showing cosine or sine. I could use cosine or sine here. I happen to be using cosine to represent the function describing the electric field as it propagates away from the source, from the antenna. Okay, and then, yeah, I think that's fine. And so this is an individual charge accelerating. That can be replaced by thinking in terms of a current that is where d I dt is happening. So if the current is increasing in this direction, that's an acceleration. If it's decreasing in this direction, that's an acceleration back in the other direction. And the E fields that get set up will be opposite to the direction of that acceleration. All right, so what happens? Well, we have an antenna set up here, and as we oscillate the current back and forth, we're going to get electric fields in this orientation, and magnetic fields are shown with the blue vectors going into the page or coming out of the page. Okay, all right, questions on this, let me know. Now, when we're close to where the electric and magnetic fields are being generated, the fields can be pretty complicated. Once we get farther away, so this is kind of what they look like close to the antenna, and they have these complicated shapes to them. Once we get far enough away, it starts to look like this. It starts to look like there's regions where the electric field is directed, let's say, downwards. That's a result from a time when the acceleration of the charges was upwards. And then that's followed by an electric field that's in the opposite direction, and that's because the acceleration of the charge by this time had changed so that it was accelerating in the downward direction. Also, the directions of the magnetic field are changing right along with that. And then I'm going to say this is the direction of propagation. So to get away from this idea that it always has to have this oscillatory look to it, let's just say that's the direction of propagation. of the electric and magnetic fields away from the source. Now this pattern of electric and magnetic field we have here, this is clearly coming from a charge that's oscillating like with simple harmonic motion, because the electric and magnetic fields also are reflecting a pattern of that simple harmonic motion. So if we have charges that are oscillating vertically, then the electric fields will also be lined up vertically. And if I look at the pattern, so what we're doing is we're taking a snapshot. Again, this is the direction of propagation of the electric and magnetic fields. So the fields are propagating in this direction. The shapes happen to be wavelength, wave-like, because, well, let's think in terms of the sequence at which this happened. This electric field was generated a little while ago, right? And then this one, and then this one, and this one. And then this whole profile is moving away from the charge, and new portions of the field are currently being generated over here at the antenna. So it's kind of a history as to what, wherever the acceleration was pointing this direction, that was created at an instant when the acceleration of charges were exactly opposite. And then the magnetic field directions, again, are determined by that right-handed or left-handed looping around the antenna. So if the antenna is lined up with the y-axis, then what we're going to end up with here is the charges are accelerating in the y direction, and the magnetic fields are forming right-handed loops alternating with left-handed loops as they propagate away. And that is what's giving us magnetic fields coming out of the board during the times when the accelerations are downwards, I want to say, yeah. And then right-handed orientation into the board when the accelerations are upwards. Here are those Maxwell's equations again. So what they tell us is that you can start from the Maxwell's equations and you can derive these formulas for the electric and magnetic fields propagating away. So what they're basically saying is that you can derive the formulas for the acceleration fields of the electric and magnetic acceleration fields propagating away from the antenna. Those can be derived using Maxwell's equations. And my response to that is always, maybe I can do that, but I can already see more clearly just using these acceleration field diagrams. Okay, so for me at least, it's much easier just to work from the diagrams and the formulas we've introduced rather than going in and trying to derive this from Maxwell's equations. So here they go. They are going to go in and set up these electric and magnetic fields and set them back to where they're being derived from Maxwell's equations, and I just don't have the math skills, I guess, to follow and kind of visualize everything that's going on. Okay. All right. So again, when we get a little farther into the book, a little farther into the slides that they've provided, they talk a little bit about the speed of light. So once we have come up with the equations, the differential equations that describe the propagation of electric and magnetic fields, what they claim is that we can derive the speed of light or the speed of electromagnetic waves from Maxwell's equations. Now, what they actually mean by that what we've got in the Maxwell equations are oh, these are the Maxwell equations with all of the charges removed. Okay, so the charges are gone here. Here, the Maxwell equations are being used to describe the propagation of electric and magnetic fields once they're away from the charges. So once they're away from these charges, we can still show that the field equations still hold, and we can still come up with formulas describing how the electric and magnetic fields will continue to propagate as they travel away from the charges. So what they've got is they've got these two force constants that they've been using throughout. And at this point, let's take a look and see, it's possible to go through the derivation, and at some point what you find is you get to a point where you say the speed of propagation for these is given by 1 over epsilon naught mu naught squared. So it gives the impression that once you've determined the electric force constant and the magnetic force constant, that from that you can derive the speed of light. And as I've suggested earlier, and I'm going to repeat now, I think they got it backwards. It's not that their constant for electric and magnetic forces are being used to derive the speed of light. The speed of light is a really fundamental constant. It determines how the space and time components of space-time are put together, how they're constructed. And so that's a really fundamental constant. And then once we talk about what the properties of space-time are, then we can move on and say what forces are present in nature. And whatever forces are present have to be consistent with the way space and time are put together. And one of those forces is the electric-magnetic force. So the electric and magnetic force are clearly all part of one force. There's only a need for one force constant. So I'm going to say these are the two fundamental constants. C tells us about how space-time is put together, and K tells us the strength of the electric and magnetic forces. All right. Now, there is a relationship if we're producing electromagnetic fields, electric and magnetic fields that are propagating, and those electric and magnetic fields look like cosine functions or sine functions. So if we're oscillating the charges, simple harmonic motion, then the fields that we generate are going to look like sines and cosines. And that tells us that we have well-defined frequencies and wavelengths. Now that doesn't have to be a feature, but it turns out it is. So if we have charges that are oscillating with simple harmonic motion. And so what will happen is we'll have a well-defined wavelength and a well-defined frequency for those electric and magnetic fields, and the product of those has to equal the speed at which the wave is propagating. Now this is not a causal equation. It's not saying that the speed of propagation is determined by the wavelength and the frequency. All it's saying is that these three values, these three physical quantities, necessarily are related. It's a relational formula. They're related by this formula. So what it tells me is, if I know the wavelength of an electromagnetic field that's propagating, that I can use this formula to calculate the frequency. If I know the frequency, I can calculate the wavelength. C, however, is not going to change. C is going to be the speed of propagation. Now, when electromagnetic fields propagate through materials, the propagation effect, the speed at which the electromagnetic fields make their way through, can slow down. So there can be situations, we'll see this, I guess we'll see this in the next chapter. We're getting ready to take a look at light. So this is kind of our transition chapter. What we're doing is we're going from electric and magnetic fields and circuits and things, and now we're moving on to these long-range electric and magnetic fields that are produced from accelerating charges. And we're moving on to light, and what are the properties of light. So in any case, the speed of propagation of the light is related to the wavelength times the frequency. And here's the entire electromagnetic spectrum. So the electric/magnetic spectrum, when we have these propagating electric magnetic fields, which we're calling light, which consist of photons being radiated by these charged particles, what we can do is we can arrange these in terms of energy. Now I know this is arranged, let's see, in terms of wavelength. So it's got a wavelength scale here, and it's got a frequency scale down here, and we've been using the equation to create the scale that we have here. We can use this equation and we can plug in the speed of light for c, and that allows us to convert back and forth. But there's something that's missing on this diagram, and we'll see this when we're into the next chapter or so. Once we get moving more into the properties of light, more and more we're going to want to know what are the energies of the photons in a particular part of the spectrum. So we can start asking things like, well, let's take the visible part of the spectrum. See how narrow that is? So your eyes are really only sensitive to a very narrow range of photon energies. So the energies need to be within this narrow range in order for you to experience vision of your surroundings. Now within the visible part of light, we experience different energy photons, or different wavelength or different frequency, as different colors. Photons with the highest energy are that we can still see. We experience that as violet, and then in decreasing energy, violet, blue, green, yellow, orange, and red. So the red end of the spectrum, those are the lowest energy photons, and the highest end of the spectrum are the highest energy photons that are able to activate the photoreceptor system in our retina. Okay, so there are rhodopsin protein molecules, I guess, in there, and there's some organic molecule embedded in that. I think it's like retinol or something, right? Something related to vitamin A. And when the light comes in, the photon changes the configuration. So if you've taken organic chemistry, this is like changing a configuration, or general chemistry. And that changes the configuration of the protein, and that fires a neuron. So that's kind of the fundamental process where photons coming in activate neurons, and then the processing begins. And some of the processing is done within the retina itself. The retinas are actually extensions of the brain. If you look at fetal development, when the brain forms, these little stalks of neurons spread out and form in the back of the eye, and that becomes the retina. So a little bit of processing gets done, fair amount of processing gets done in the retina. That information goes back into the brain, further processing takes place there, and as you probably know, the visual processing center is pretty much at the back of the brain, right? Where the visual processing, and somehow from all that, we have the experience of vision from those neurons being fired. All right, so let's take a look at the spectrum that we've gotten ourselves into. Let me check the time real quick too. So make sure that we get a break when it's sensible to get a break. We've got some time here. We're doing pretty good. So what we've got here, let's see, at the lowest energy photons are in what we call the radio part of the spectrum. And again, we don't have to call them radio waves, just say it's the radio part of the spectrum. Those are the lowest energy photons. And then at some point, and this is fairly arbitrary, so you see there's kind of overlap in terms of what we call radio and then what we call microwave. So microwave, the micro in microwave, means the shortest wavelength radio photons. And so these are a little higher in energy, and then at some point we stop calling them microwave. Once they have enough energy, we start calling them infrared, And then again, we hit the visible spectrum portion of this completely broad spectrum of photon energies. And then once we get more energetic than visible light, we hit the ultraviolet region, and then at some point we call those X-rays. When we get to the highest energy photons, we call those gammas. Okay, so gamma photons, that category is reserved for the highest energy photons. So think about this. If we had electrons or protons, if I had a high energy electron and a low energy electron, I would still call them both electrons. But if I have a high energy photon or a lower energy photon or a medium energy photon, we have all these different names: gamma, X-ray, UV, infrared, visible light, microwave, radio. Okay. All right, so that's the story with these electric and magnetic fields that are being propagated then. Depending on what... So there's going to be a range of possible energies for these photons, and depending on what their energies are, they will have different frequencies and they'll have different wavelengths to them as we move back and forth along the spectrum. So very quickly, energy, high energy, correlates with high momentum, correlates with high frequency, correlates with short wavelength, and then all the vice versas. So long wavelength correlates with low frequency, low momentum, and low energy in terms of properties of photons, properties of light. Okay, here's a problem we can take a look at. Here we are determining wavelengths of some propagating electromagnetic fields, and it says, what about a frequency of 60 hertz? And then it says, what about a frequency of 93.3? It's some FM radio station. And then it says, what about a beam of visible light? And it's in the red part of the spectrum, and it's at a frequency of 4.74. Times 10 to the 14th hertz. Okay, so we said here is a representation of these purely sine or cosine fields. So here are the electric and the magnetic fields being produced by this in these kind of perfect oscillations. And this is referred to as a plane wave setup. The features of this is that they're propagating at the speed of light. The electric fields and the magnetic fields are perpendicular to each other, and they're also mutually perpendicular with the direction of propagation. So those are three vectors that are all mutually perpendicular. Now here is our statement of the wavelength times the frequency is equal to the propagation speed of the fields. And so I can put in these frequencies. Now 60 hertz is really low. I switched radio stations. I didn't know what 93.3 was, so I put in 88.5 KQED. That's a good radio station, right? Public radio. And so I'm just calculating the wavelengths from here, taking C and dividing through by these frequencies. And it says this. It says that now 60 hertz, that's the frequency at which our electrical devices that we plug into outlets. Outlets are set up, we generate electricity, so that it's alternating at 60 hertz. So when we plug something in, there's going to be current inside those cables that are where the charges are accelerating and they're oscillating back and forth at 60 hertz. Now, what would be the wavelength that's being produced by that 60 hertz signal? And putting the numbers in here, oh my gosh, the wavelengths are 5,000 kilometers. Okay, those are some really long wavelengths for the light, the really, really low energy photons that are being produced by alternating currents in our circuits. Now let's move up. This number is like 1,000,000 times bigger. So the signals coming in from KQED radio have a wavelength of 3.39 meters. So that's more imaginable. So 3.39 meters would still, that's going to be 11, 12 feet, something like that. So what that's saying is, if I take a snapshot of the electric field pattern, what I'm going to see is that the electric field varies from being 0 to some highest value, to some 0, to some lower value, to some... So for a full cycle, that looks like a cycle, oh, there it is. That looks like one full cycle. For KQED signal, it's 3.39 meters per one cycle. Now that cycle, the profile of that electric field is propagating away from their antennas at the speed of light. And so this pattern of electric fields is propagating. Another thing we want to be really clear with when we talk about electric and magnetic fields propagating is that when we do these drawings, there is nothing oscillating like this. What it's saying is that at these locations in space, so at this point, the electric and magnetic fields are what we call plane waves. And that means that if I take any direction pointing away from where the electric and magnetic fields are coming from, if I look at the direction of the velocity, what I can do is I can imagine a series of locations. And at this location, the electric field is pointing in the direction up, and it has this much magnitude. And then here, it's also pointing up, pointing up, pointing up, pointing up, pointing up. There's nothing physically distanced here. This is just showing the magnitude of the electric field. So what it's saying is, if I sample the electric field at a series of locations, I will find that the electric field here is pretty small, but here it's larger, and here it's larger, and here it's kind of peaks, and then it comes back down. Now if I come down here and do the same analysis, I will find the same pattern. So when we draw these vectors in space, it's easy to get confused and think that the length of the vectors are actually indicating distance, and they're not indicating distance. They're indicating the magnitude of that electric field at just one location. So drawing all these electric field vectors in are only telling us what the electric field value is at a series of locations that we've mapped out. Okay, so again, nothing is rising and falling. It's just at different locations. It's like writing down a bunch of numbers. So I could write a number here and say this is 2, and this is 5, and this is 7, and this is 8, and this is 6, and this is 2, and this is 0, and this is now -2, and this is -4. But again, I'm just referring to values that I will run into as I follow that one particular path, is what this is keeping track of for us. Okay. Ooh, here's one more attempt to show what's going on, right? So here's the antenna, and I have charges moving back and forth here. Oh, this is the radio station. I was trying to read that, but I think it's just a radio station and there's windows. I noticed that over here, what we have is, I've got my radio out. I got my radio out, and I'm listening to my radio. I'm picking up a radio signal. And the radio station over here, they have an antenna, and they are oscillating charges, and they're actually using a particular pattern. So they're embedding a pattern of oscillation. They're varying the oscillation just a little bit so that the signal is encoded. So the signal, it's not just a pure sine function, it varies just a little bit. Now my radio knows how to decode that. So my radio knows how to take the signal that has been sent by the radio station. So here's the electric field, and here's the electric field, and here it is, and here it is, and here it is, and here it is, and that whole pattern is propagating right past my radio antenna. So what that does, kind of interesting, kind of remarkable, the pattern of oscillation that the radio station produced will be replicated in the antenna of my radio. So whatever varying current that we use to generate the electric fields and the magnetic fields, those electric fields will then, when they encounter an antenna, will oscillate the charges, oscillate the electrons in that antenna with the very same pattern that they were generated with. Okay. All right. So I've also got magnetic fields in here too. So the magnetic fields, those are the X's going into the page, out of the page, into the page, out of the page, into the page, out of the page. And then this whole pattern sweeps over my antenna, and the antenna electrons follow the very same pattern that was generated by the radio station in their antenna. And this can be a long ways away, as you guys know. So, yeah, that's something to stop and think about some, huh? So I'm going to say, again, my favorite radio station, KQED, so that's going to be a frequency of 88.5 million hertz. That's the oscillation frequency from the antenna. The wavelength is 3.39 meters. Oscillating, accelerating charges are generating oscillating electric and magnetic fields. Okay, I'm going to stop there. I think that's a good time for a break right there, and then we'll come back and finish out the chapter. We'll take a look at the rest of the chapter and see what we got.